Good morning, all. I will start with a correction of the day. So we hit this thing, and then I wrote one equality on the board which was wrong, and I want to correct it. So what we can do is we can take the, rather than taking both expectations at the same time, we can take the expectation with respect to y, and then we can take the expectation with respect to x of our function of two random variables. And now we condition this on y. Then we obtain something which depends on y only, and from that we can take the expectation. Yeah? So this is the correct version. And this is one of two things I had written on the board. And if we want to flip it around, so we can also say this is the expectation of x with respect to y, and then here I need to condition on x. That is also correct. But I think I wrote a garbled version of this on the board last time. Yeah? So this is what works. All right, thanks again for spotting. All right, and today we will look at the left and the right-hand side of Bayes' theorem in the context of classification. So we will look at generative and at discriminative classifiers. And for generative classifiers, we will use, so last time we were discussing options. If we want to focus on the right-hand side, how could we estimate the quantities involved? And one of you suggested, let's take a parametric model, this. Maybe the first idea would be to use a Gaussian for each class. And indeed, this is an important method. This leads to quadratic discriminant analysis. And this is what I want to discuss first. And later, we want to look at the left-hand side at methods that directly predict the class label given some features without bothering to estimate any densities involved. And those empirically in most settings are, as classification goes, the more broadly used and more successful methods nowadays. And as a first representative of the family, we will look at the decision trees and ensembles of decision trees, which still are state of the art for tabular data. Okay, but we look first at quadratic discriminant analysis, and even before we look at quadratic discriminant analysis, let's look again at the Gaussian distribution, or the normal distribution, as statisticians like to say. So we have some mean, we have some inverted covariance matrix, or so the thing, if we take it to the inverse, is also called the precision matrix. All right, and then we have, so this part you must know by heart. The normalization constant you do not. And so if we have dimensionality of p, this is the small p that I mean here for dimensionality. All right. So there's a normal distribution. And here is the inverse covariance matrix. And our the way we estimate it from data is by using empirical estimates of what I'm writing here. So here X would not be a matrix, but it would be, if I write a capital X here, what I mean is a vector, a random vector. So a random variable which happens to be a vector. And okay, and the convention I'm using here is to say that this thing is p by 1. So this entire thing here is p by 1. Okay, and then this entire thing here would be p by p. And this is the sigma that we're talking about here. And if we only have a finite sample, then we replace these expectation values by the sum over all samples, and then we divide by 1 over n. Okay. And there's an interesting story about this part here, because the matrix inverse has the property that if we use a sparse matrix and we invert it, then it becomes dense. And this is something that's exploited in Markov random fields, where we specify dependencies only between adjacent nodes in our Markov random field. But this then, by taking the inverse here, this propagates, and this leads to correlations throughout the entire network. So this is why Markov random fields are a very economic way of characterizing the behavior of fields of random variables. And this was a super important class of methods before neural networks steamrollered everything. Yeah? Which is a pity, because there's beautiful mathematical theory associated with it. But hey, we're also pragmatic and use what works best. All right, and here a few pretty pictures. So what we have here are isocontours of a few Gaussian random variables, and the parameterization chosen in this picture here is to say that we have this matrix here, and you see small things in the legend, yeah? And we have these variances for these 2 dimensions along the diagonal, and then we have there's a row here. We have rho times sigma 1 times sigma 2 on the off diagonals. And what we see here, in each column, we have the identical margins. Same margins or marginals, also here and here. What is a marginal? So if we have a probability density which depends on 2 variables, then we can integrate out one of them, and then we obtain something which only depends on this other variable, and that would be the marginal here. So if we integrate, for example, if we integrate out the x2 dimension here, then I obtain a 1-dimensional Gaussian as a function of x1, and that Gaussian would be the same here, there, and in the top picture. Same argument here. We get the identical marginals for the x1, and we get the identical marginal for the x2, even though, of course, they look different. And this tells you what additional information is in the covariance matrix. And well, the Gaussian, it's popular for many reasons. One is that compared to more general distributions, or more flexible descriptions, we need relatively few parameters. So we only need the first two moments to, well, specify the entire distribution. Okay. And the picture on the bottom you see, I really like stack exchange. There are sometimes very subtle discussions of interesting questions. And then the main difficulty is to not get sidetracked by the panel on the right-hand side. I don't know, do we have any stack exchange users here? At least one person knows what I'm talking about. You know, you want to think about this, and then on the right-hand side, there's a discussion of, you know, what did this switch on the Apollo 13 mission do, and why did the astronaut put a sticker with no, you know, across it? And well, if you want to know, you need to go to Stack Exchange. All right. But these random variables here, they are special in that this one is Gaussian and that one is Gaussian. I believe this one is too. And all of the ones that you see here, they have the identical marginals. And these marginals, for all of these distributions here, they're all Gaussian. Yeah, so let's think about this funny example here. If I integrate out here this first dimension x1, I get something which is beautifully Gaussian, along its marginal here, and it's also beautifully Gaussian along the other side. And that holds for all of these contrived examples. So from this, we see that there are certain conclusions that we must not draw, and I want to spell these out. So for normal distributions, which, by the way, you will also have this kind of notation. The exercise sheets, statisticians, they like to use a script n for this. So what we have is that the marginal of a normal is normal. What we have is that the conditional distribution of a normal is normal. So conditional distribution means that if we clamp one of the two to a specific value. Yeah? So let's say we have some Gaussian distribution. And now I'm clamping, for example, x1, and then I'm left with a random variable. So I then still have, okay, so let's say x1 is clamped to some specific value c, and this is now still a random variable over x2, and you can see that this random variable will have its mean around here, and it will have standard deviation of its own, which is not the same as the variance of the original distribution. Yeah? So here now we condition on this line. We only look at what is our distribution doing on this line, and we forget everything that's on the right or the left-hand side. Yeah? So this is what's meant by the conditional distribution. And the marginals, well, we can take them by projecting onto the coordinate axes, but in our discussion about double descent, we projected the Gaussian onto some, so we said we initialize at 0, but then we projected it at some slanted plane, and of course that also was a Gaussian. So what we also have is that the product of normal distributions is normals, is also normal. Product of normals is normal. Now comes the but. And that's what the picture here wanted to show, that normal marginals do not imply do not imply a jointly normal distribution. Okay, and what we just saw on this stack exchange example was were a few examples. Okay, so so much as a reminder for the normal distribution, and now we will use this to estimate or to approximate our densities for to construct a generative classifier. The technique is called Quadratic Discriminant Analysis, QDA for short. And the argument goes as follows. So we have we take this term here, which is the class density. And in QDA, all these class densities are modeled by normal distributions. And now we can ask for the decision boundary. So if you look at textbooks on classification, or if you watch videos and so on, you always find these sort of pictures. So we have two classes here, they intersect a little bit. And okay, now we're trying to construct a classifier here. And what happens is that here we try and model this one, let's say the crosses, with a Gaussian distribution, and we try and model the circle class with a Gaussian distribution. So I'm finding the mean, I'm estimating the covariance matrix, and I pretend it looks something like so. And now the question is, what will the decision boundary look like? And well, because these are isocontours, I can intersect the respective isocontours. So I am taking the, I have 3 isocontours for each, so I'm intersecting the outermost ones. I'm intersecting the second ones. And the first ones don't touch. So I am getting here a decision boundary which looks something like so. And now an interesting feature is, you see this red class, it penetrates the green one, right? This is like, it is elongated in this direction. So in this direction, the red class has bigger variance than the green one. And this means that eventually, as we go far away, the red class will win again. So I will have another part of the decision boundary which lies up here. Yeah, so what this decision boundary tells me is that it says here be green. And it says that here be red. And it says that here also be red. Now that's interesting. I mean, this is not very much supported by the training data that we have here, but it is what follows if we use a Gaussian model for each class. Yeah, so this is the kind of fallacy that is involved if we use parametric models that don't really fit the data, or if we try and make predictions that are far away from the training data. The same goes, of course, for neural networks. Yeah? So our neural network, let's say we use a fancy transformer, huh? If we have enough training data, it will do great here. It will produce absolute garbage elsewhere. And this is why it's so important to have some controls built in. Yeah? So some kind of outlier detection or some other means of detecting when you're too far away from your training data. All right, but here I painted these decision boundaries freehand. So how can we find them? Yeah? And the way we find them is by saying, so for the 0-1 loss function we discussed last time, we are always asking which class is locally dominant, and the decision boundary is where the two classes or where the two posteriors are equally strong. Yeah? So I can ask for the set of points where the probability that my class is 1 given x is the same as the probability for class 2. And so this gives me a condition on the x, and now we use the right-hand side. Yeah? So we are asking for, so I can write this a bit shorter and say the probability of 1 given x should be the probability of 2 given x. And now we invoke Bayes' theorem here and use the right-hand side. Okay, I need more space. Okay, so we took that and we inserted the right-hand side. We see that the numerator, the denominator cancels, and we can, write down explicitly what this would be. So I put a normal here. This is my normalization constant times the prior, and a very similar looking expression on the other side. Okay, now we try and solve this for x. So we can do C1 divided by C2 times P of 1 divided by P of 2. And then I have these exponentials, so it will be good to take a logarithm here. And if I do take the logarithm of this product, this will turn into a sum. So here I can write minus 1/2 x minus mu1 and then there's a minus here, it comes over with a plus. The x is gone. Good, and this should be 0. And so what we have here is a scalar, or maybe it's nicer if I multiply this with a 2. Okay, then what we have here is a scalar, and what we have here is an expression which is, there are products of x appeared, so this is an expression which is quadratic in x. And functions which are quadratic in x, they have a name in geometry, those are the quadrics. Okay, and what quadrics do we have? We have paraboloids, or we have hyperbola. We have certain degenerate cases like crossing lines or parallel lines. If we look at the isocontours, that's what the quadrics look like. Let's look at pretty pictures. Let's look at the wiki page for this. Actually, I do donate to Wikipedia. This is my #1 donation. Because I think it's, they don't have the option, no, I do already. Because I think it's a great democratization of knowledge, and I love that it has no, advertisements and crap. Okay, so here you see in 2 dimensions what isocontours can look like. We have circles. Think for a moment, what class densities would produce a circular decision boundary? Any suggestions? So I use 1 Gaussian for each class, and the result is a circular decision boundary. Yes? They have to have the mean at the same point, and different variance. And can you say one more thing? Because that would still allow arbitrary shape, right? You just say one has to be has to have a bigger variance than the other one. Okay, I'm trying to give a counterexample. Yeah? So let's say this is my first, and this is my second one. I think you're thinking about the right thing. I just want to insist. So this one here is, more compact than the other one. But the decision boundary here would be elliptic. Remember again that normal distributions are not always spherical. Yeah, isotropic. Well, same variance is still not enough, yeah, because this one here has the same variance in both dimensions, the white one, yeah? We need to insist that it be isotropic. So it has to have a diagonal covariance matrix where all entries are the same. Yes, that's what we would call, isotropic or isotropic normal distribution. And then you're completely right. Your observation was right. The means need to coincide. They need to both be isotropic and they need to have different variance. Yeah? So we have two isotropic normal distributions. One is compact and the other is diffuse. And this gives me a circular decision boundary. Right. Okay, we can have elliptic decision boundaries. That's the yellow one. We can have parabolic decision boundaries. That would be green. And we can have hyperbolic. And that, what I showed here initially was an example of a hyperbolic one. Now this is just in 2 dimensions. As we go to 3 dimensions, you see that what decision boundaries could look like, yeah? And it has a, I would say the expressive power, or how should we say, is not so bad, right? Especially if you have little training data, those can be decent approximations to the real thing. Let's look at more pretty pictures. All right, so what we have here is the problem from last time. And I failed to find a pointer without a broom. Anyway, so I invented this class density here. Just to make sure, it doesn't look boring like a normal distribution. I invented that class density, and we were discussing, what's the very best conceivable classifier there is in the whole world. If we know the true class densities, it is the base classifier, and its decision boundary is here shown in green. And this was sample data drawn from this true underlying distribution. Now, I have used this same identical training set, the one you see it here on the left-hand side. And now I use this training set to estimate the 2 class densities using Gaussians, using normal distributions. Yeah, and so you see the red class here is relatively diffuse. So its class density multiplied with the prior looks like so. The blue class is relatively compact. So this is normal distribution, which looks like so. And now if we put it into Bayes' theorem and look at the posterior, then this is the posterior, or this is 1 minus the upper picture. And the decision boundary is given by the set of points where both classes have the same posterior probability, 0.5. So I'm looking at an ellipsis here, and there it is. Yeah, here's my ellipsis, or here it is shown relative to the training data. And here I would actually say, I would be pretty happy with this decision boundary. Compare it to the Bayes classifier. The Bayes classifier was this, but I argued, this tiny annex here, it's practically impossible. Yeah, there are not even blue points in there. So how am I supposed to find this annex? And if I, squint, I can say this looks largely like a ellipsis. And there you go. Yeah. All right. So I would say for this dimensionality, for this amount of training data, not a bad model. More pretty pictures this time from an old school book by Dudehart and Stork. It's old but nice. And it came out in the 70s, and then this here is a rehash from around the 2000s. But it was, I think, the first good book on machine learning out there. All right, and here are pictures from this book on what the distributions and the decision boundaries could look like. So you see on the top of these plots a red Gaussian and a gray Gaussian, and the rendering here is in an opaque fashion, so we always see only the one which is which occludes the other one. And shown below are the decision boundaries. So here, for example, we have this parabolic decision boundary. Here we have an elliptic decision boundary. Up there we have a degenerate case, two intersecting lines. On the left, on the top left, another degenerate case, two parallel lines for our decision boundary. Here a hyperbola, and here a circle, I believe. Okay. Good. So we see that we get quadrics. And so far this is, all good. However, when I said it has few parameters, well, as the dimensionality grows, things don't look so great. So if our dimensionality small p is large, we have very many parameters. So P sometimes is probability, but here I use P for dimensionality. Because, well, we have to estimate the means for our classes. We have mu1 and mu2. And we have these terms in particular. Yeah, we have our covariance matrices. They're symmetric, but each has P squared parameters. So of the order, yeah, P times P minus 1 over 2 parameters. And if we have too few points in too many dimensions, this is unaffordable. So how can we, reduce the hunger for parameters? Or how can we make this method applicable if we have, let's say we have 100 points, but in 10 dimensions. If I do it naively, 100 points in 10 dimensions, this already will have 50 of the order of 50 parameters, and then this will have another 10, this will have another 10. I would not feel so comfortable. How can we make the method less flexible? Yes. The suggestion is to use PCA for dimensionality reduction. That would work. And it's related to some other suggestions that are possible. Do you have other ideas? If you look at this formula here. But PCA would work, yeah? The suggestion was to diagonalize, or let's say we can impose stronger assumptions. Yeah, because anyway, saying that each class is normal distribution, that's a very strong assumption. Yeah, and now we can make the assumptions even stronger. Yeah, so we can say, for example, so too many parameters. So what we can do is to reduce flexibility, what we can do is, okay, now we can do a laundry list of things we could do. We could assume that sigma 1 is a diagonal matrix. That's what you suggested. And we would have the same form for sigma 2. Yeah? That drastically reduces number of parameters. That's correct. Do you have other suggestions? You know, more drastic. Yeah. Exactly. Yeah. We could assume that sigma 1 is sigma squared times the identity matrix. And sigma 2 would be sigma 2 squared times the identity matrix. Okay, even stronger. Yes? Exactly. As we can say sigma 1 equals sigma 2 equals sigma squared times the identity matrix. Yes. And there is another one which is a bit more subtle. And in the order of assumptions, I should have put it up here. I'm sorry. People with a tablet can, you know, move this down. I can assume that sigma 1 equals sigma 2, but is not necessarily so sparse. And if we assume that sigma 1 equals sigma 2, then, you know, here we have this quadratic term, x precision matrix 1 times x. And here we have, and there was a minus, and then we have the same term with a plus, yeah, plus x precision matrix x. And if sigma 1 equals sigma 2, the quadratic term cancels all together. And in this case, so quadratic term cancels. And then the method that we get out, and this here is a special case, yeah, because also here sigma 1 was sigma 2. What we get then is something which is called a linear discriminant analysis. This, or LDA for short. Okay, and when you read LDA, you need to be careful because terminology in machine learning is overloaded, and LDA is also used in a different context where it means latent Dirichlet allocation, which is an important topic model. This LDA is a lot fancier than that LDA, a lot more interesting statistically, but it's something entirely different. Yeah? So when you read LDA, probably people nowadays are talking about this, but you need to, you know, yeah, look at the context to find out what is meant. Okay, so what we have here for QDA in summary, is it is a parametric model because the number of parameters does not grow with the size of our data set, and it is a generative model. We were modeling the right-hand side, we were modeling the class densities. It's a parametric generative model for classification. And yeah, should you use it? I would say not using the full flexibility in the parameters, except if you have lots and lots of training data. So in higher dimensions in particular, you will need to make some of these assumptions. So I would say it's relatively parameter hungry. And it only works for observations on the interval scale. And sometimes all your measurements are on the interval scale, but sometimes are not. Yeah? So sometimes you have categorical or nominal features, and QDA will not know what to do with those. But the methods that we will discuss after the break, they do. However, before the break, we come to announcements.